Okay, hi and welcome back. Today we're going to continue our exploration of advanced integration techniques. Today we're looking at trig substitution. Interesting. So this is, when I learned this, I was mind blown at how you could actually do this. It's just so creative and something I never thought about. But with that said, it is a little bit tricky. But the good thing is that this only applies to some integrals that have a certain form, a certain pattern. So if you detect that pattern, you can use trig substitution. Let's look into it. We'll take some time to iron everything out, make sure we understand it, and as always, do a couple of practice problems. Here we go. When and how to use trig substitution. If you have an integral resembling one of these three forms, the square root of a squared minus u squared, or square root of a squared plus u squared, or the square root of u squared minus a squared, then we can use trig substitution. So in this case, a is a constant and u is some function of x. So u could be 3x or whatever like that. So an example of a squared minus u squared could be 9 minus 16 x squared, where we have a equal to 3 and u equal to 4x. So u is a function of x, a is a constant. And what we're going to do is use triangles, the Pythagorean theorem, and trig functions. So let's take a look at the first case where we see something with the square root of a squared minus u squared. What we can do is imagine a right triangle with these sides. One side length is going to be our a squared minus u squared. The other side length will be u, and the hypotenuse will be a squared. And if you check the Pythagorean theorem, sure enough, this holds true, which is good. So we can imagine that we have this kind of triangle, and keep in mind the technique we're using is called trig substitution. So if this is what we find in our integral, we're going to substitute that with some sort of trig function. So actually what's going to happen is we're going to change our function from being in the x or u world, where u is some function of x. We're going to change it to be in the theta world. So notice how we call this angle theta. If we take sine of theta, that's equal to u over a for our triangle, which means that u is equal to a sine of theta. And this is good because we can also get cosine of theta being this over that, and we get a cosine of theta is equal to the square root of u squared minus a squared. So we see this, we can substitute it now with a cosine of theta, but since we're doing a change of variables, we'll have to change du to be in terms of theta. So we have this u equals a sine of theta, we can solve for du that way. It may sound a little bit confusing, we'll do an example together in just a moment, but that's the general idea. Get rid of this nasty square root thing by converting it into the world of theta using a trig function, trig substitution. In the case we see a squared plus u squared square root, we do a similar thing. Construct this triangle. Notice the side lengths are a little bit different now. We have a squared plus u squared, that square root on the hypotenuse, and then the legs are u and a. Now we'll consider the tangent of theta, and we can conclude that u equals a tangent of theta. This will be helpful in calculating du. And if we consider the secant of theta, that's equal to the square root of a squared plus u squared all over a. And because of that, we can solve for the square root of a squared plus u squared equal to a secant theta. So we can do this substitution, solve for du, get it in terms of theta, do all of those substitutions, and we'll be in the world of theta. Lastly, if we have the last form, the square root of u squared minus a squared, form this triangle. Now we can consider the secant of theta, which is equal to u over a. We have u equals a secant of theta. And if we consider the tangent of theta, it's this fraction, which means the square root of u squared minus a squared equals a tangent of theta, and do substitutions as necessary. Let's see an example actually solved so we can see how these things piece together. So this is our integral. 1 over x squared times the square root of 9 minus x squared. we see that square root in the denominator, and we see that it's of the form a squared minus u squared, where a equals 3 and u equals x, right? If you substitute a equals 3 and u equals x into here, that'll be the square root of 9 minus x squared, which is what we see right here. So that means we are of this triangle here. We're the form of this triangle right here. So we can calculate sine of theta and u accordingly. Let's first look at that triangle. This is what the triangle looks like, and indeed the Pythagorean theorem checks out. If we take the sine of theta, that's opposite over hypotenuse, that's x over 3. So x equals 3 sine of theta. Solving for dx, we get 3 cosine of theta d theta. Now we can take the cosine of theta to get the square root of 9 minus x squared over 3. And since we're targeting to substitute in for this square root of 9 minus x squared, we'll solve for that and say that's equal to 3 cosine of theta. Now when we get back to this integral, where we see the 9 minus x squared, the square root of 9 minus x squared, we can substitute that with 3 cosine of theta. We still have this x squared term, but we need to be in the world of theta. Luckily, we solve for x up here, so that can get substituted in. So x squared becomes 3 sine of theta quantity squared. And then finally, the dx has to be changed to the world of theta, which we solve for over here. So that gets plugged in for 3 cosine theta d theta. Now we have an integral where everything is converted into the world of theta, and we can solve for it in terms of theta. This 3 cosine theta cancels with this 3 cosine theta in the denominator. We're left with 1 over 3 sine theta squared d theta, which is equal to 1 over 9 times cosecant squared of theta d theta. That is equal to negative 1 over 9 cotangent of theta. But since the problem started in the x world, we have to go back to the x world. So what is cotangent of theta? Well, for that, we can just look at our right triangle here. And that will be adjacent over opposite. So square root of 9 minus x squared over x. So we substitute that in for theta, and we get our final answer here. That's the general pattern. Take our integral, convert everything to theta, solve for it in terms of theta, then convert back to x. That's the general pattern. That's what we're going to be following. Let's try to solve a problem on our own. We have the integral of 1 over square root of 4x squared plus 1. Okay, and we see that it is of the form of u squared plus a squared, right? Square root of 4x squared plus 1, we can rewrite that as the square root of 2x quantity squared plus 1 squared. So we can pretend u equals 2x and a equals 1, and we're of the form u squared plus a squared. That's what we're dealing with here. Okay, so now let's construct a triangle. Does this work? Oh, it does. Let's go. Okay, so we have a right triangle where this is going to be theta, and we know we want one of the side lengths to be square root of 4x squared plus 1. And you can look back at the slide previously where we had those triangles, but it's also good to get in the habit of thinking what the side lengths should be. And we know we're going to need to use the Pythagorean theorem to get like the side lengths. So we can see that this 4x squared plus 1 is like reminiscent of this a squared plus b squared. And to get c, we would take the square root of that. So it seems like c will be equal to 4x squared plus 1, square root of that. So we can put this here. And then the other terms will just, the other side lengths will just follow. We have a 2x and a 1 to deal with. So we'll put 2x, 1. So you may be curious, why did we put 2x here and 1 here? And honestly, it doesn't matter. You can switch them however you want. And the reason for that is because, as we saw in the examples prior, we usually take two trig functions when dealing with this triangle. Either we do sine and cosine, or tangent and secant, and both of those come into play when computing the integral. So no matter how you arrange those two sides, all of the terms will show up eventually when you're taking either the tangent and secant or the sine and cosine. So the ordering of those two side lengths don't really matter. So we'll keep them as 2x and 1 for now. Okay, so if we scroll back up to here, we're underneath this second column here, and we computed tangent of theta and secant of theta. So let's do that with what we have now. Tangent of theta, tangent is equal to opposite over adjacent. So opposite of theta is 2x, adjacent is 1, so tangent of theta equals 2x. And secant of theta, secant is 1 over cosine. Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. So this would be the square root of 4x squared plus 1 all over 1, which is equal to the square root of 4x squared plus 1. Which is good because we want to substitute that 4x squared plus 1, so we can change that to be in the world of theta by letting it equal secant of theta. But we would also have to change that dx to be equal to something with thetas. So for that, we can turn to this tangent of theta being equal to 2x and take the derivative of both sides. So the derivative of tangent of theta is secant squared theta d theta, and the derivative of 2x would just be 2 times dx. So now when we return to our integral, the integral of 1 divided by the square root of 4x squared plus 1 times dx can be rewritten as the integral of 1 over secant of theta times dx, which would be equal to 1/2 secant squared theta d theta. Right? So now we are in the world of thetas, which is good. And we can see that things cancel out really nicely. This becomes 1/2 integral secant of theta d theta. And we know what the integral of secant of x is, so this is just the same thing now with thetas. So that will be 1/2 times the natural log of the absolute value of secant theta plus tangent of theta plus c, because it's an indefinite integral. And although it looks like we're done, there's still one more step to do. Remember, the outline for these problems is change things to the world of theta, integrate, and then change back to x's. So we have to convert this back to the world of x, which means wherever we see a theta, we can replace it with something with x's. So we can compute secant of theta, but in fact we already have up here secant of theta equals the square root of 4x squared plus 1. And tangent of theta we also computed up here, that's just 2x. So this all simplifies to 1/2 times ln absolute value 4x squared plus 1 plus 2x plus c. That is your answer. Isn't that cool? This is just such an amazing technique, something like I would have never thought of. Imagine you're the first person to come across this integral. And the way you solve it is by introducing some trig functions, drawing a triangle, changing it to thetas, and then going back to x. This doesn't even seem like it needs a trig function in it. But it does. And my favorite part about it all is that the final answer doesn't even look like it has a trig function in there. It's completely mysterious, but it is beautiful. Absolutely gorgeous how this works out. There you go, that's our first walkthrough example of trig substitution. The good news is that all of the other problems are very similar. It's a similar pattern. You just need to know how to construct the triangle and just do your substitutions as always. So let's do it. Here we have a definite integral from the square root of 3 to 2 of the square root of x squared minus 3 over x dx. Okay, so if you were to see this for the first time, you might be tempted to do u substitution, right? It seems so tempting to let u equal x squared minus 3 du equal 2x dx, and then this converts to the integral of the square root of u over x times du over 2x. Oh no, it doesn't cancel. The x's don't cancel. That's not good. And then you're like, okay, well, maybe I can change the x to be equal to the square root of u plus 3, but that's just nasty. That's just not fun to work with anymore, and you'll be stuck to where you were before. So u substitution's not going to work. Integration by parts, I don't want to do that because there's a square root there. That's not fun. And you're like, well, so it's probably trig substitution because we're in that unit. But this doesn't really look like any of the square roots that we wanted. Remember, we're after square roots of the form u squared minus a squared, or a squared minus u squared. I'll just leave it at those two since we have the minus sign. And we can pretty much eliminate the second one because the function of x is the first term. 3 is not a perfect square. So what? Who cares? If we let u equal x and a equal the square root of 3, we're in business. It's still of that form, square root of u squared minus a squared. I don't care that 3 is not a perfect square. We can still do some trig substitution. Let's do it. So we have u equal to x, a equal to the square root of 3. As we saw in the previous example, those values kind of contribute to creating our side lengths. So we have this right triangle here. This time this x squared minus 3 won't be on the hypotenuse because there's a minus sign there. So we can put one of the lengths as x squared minus 3. And then you can test out the other values. One should be x, the other one should be square root of 3, and the only way it works is if the hypotenuse is x and the other leg is the square root of 3. Cool. Let's just scroll back to see which column we're under. It's this one, so we'll need to compute secant of theta and tangent of theta. So let's do that. Secant of theta is equal to hypotenuse over adjacent. I always forget this, so I need to say it out loud just to help myself. So this is x over the square root of 3, and we can solve for x by saying x equals the square root of 3 times secant of theta. Good. Tangent of theta is equal to opposite over adjacent, so this is the square root of x squared minus 3 all over the square root of 3. Okay, and then we can solve for the square root of x squared minus 3 because that's kind of what we're looking to substitute by saying that the square root of x squared minus 3 equals the square root of 3 times tangent of theta. Good. So now we have to think about our substitutions. We can substitute for that because we solve for it here, but we still need to solve for x and dx. Well, we've already solved for x over here, so we can convert that into the world of theta. We need to change dx into something with du. So for that, we can take the derivative of this equation right here. So on the left, we'll get dx, and on the right, we have to take the derivative of square root of 3 times secant of theta. So that'll be square root of 3 times secant theta tangent theta d theta. Now we're in business, we can substitute. Okay, so let's now solve this integral. And I'm going to use colors to indicate what's going on. So we have the integral from square root of 3 to 2, and the numerator is the square root of x squared minus 3. We're dividing that by x and multiplying that with dx. So we have our colors, we're ready for substitution. This is equal to the integral. I'm going to leave off the limits for now because we're changing into the world of theta. So the numerator now becomes the square root of 3 times tangent of theta. The denominator becomes square root of 3 times secant of theta. And dx becomes the square root of 3 times secant of theta times tangent of theta times d theta. Let's change the limits from being in the world of x to the world of u. So we'll deal with the lower limit for now. We had x equals the square root of 3, and we want to know that what does theta equal in that case. So for that, we can look at the equation secant of theta equals x over the square root of 3. That comes from our triangle, which means that secant of theta should equal the square root of 3 over the square root of 3, which is equal to 1. So secant of theta equals 1. Maybe you know that off the top of your head. I don't. So you have to think secant of theta is 1 over cosine of theta, which means cosine of theta should equal 1. When does that occur? When theta equals 0. So that'll be our lower limit. For the upper limit, x equals 2, what does theta equal? Again, we can look at secant of theta, which is x over the square root of 3, which is now going to be 2 over the square root of 3. That tells us cosine of theta should equal square root of 3 over 2, and that means theta should equal pi over 6. So we can write in our limits now. Our lower limit is theta equals 0. Our upper limit is theta equals pi over 6. Let's simplify this integral a little bit so it's a bit cleaner. Integral from 0 to pi over 6. The square root of 3's and the fraction cancel, so we're left with tangent of theta over secant of theta times square root of 3 times secant of theta times tangent of theta d theta. The secants cancel, so it's 0 pi over 6 of the square root of 3 times tangent squared of theta d theta. Well, how are we going to integrate this integral of tangent squared of theta? For that, we can turn back to our previous video on integrating trig functions of higher powers, look through the guidelines, and you'll note that we can convert tangent squared theta into secants by using the trig identity, where tangent squared of theta equals secant squared of theta minus 1. So this is equivalent to the square root of 3 times the integral from 0 to pi over 6 of secant squared theta minus 1 d theta. This integral can break apart into two integrals. I like to do that because it keeps things clean for me. And this second integral here should be pretty easy to solve on our own. But the first integral, the integral of secant squared of theta, is simply just tangent of theta. So this will be equal to the square root of 3 times tangent of theta, evaluated from pi over 6 down to 0, minus square root of 3. The integral of 1 is simply just theta, because we're in the world of theta. And that's evaluated from pi over 6 down to 0. Now we can use our fundamental theorem of calculus to get that this is equal to the square root of 3 times tangent of pi over 6 minus tangent of 0 minus the square root of 3 times pi over 6 minus 0. Note that we do not have to switch back into the world of x's. In the previous problem we did, because it was an indefinite integral, and we had to represent our answer in terms of x, because we know for indefinite integrals it's going to return an expression, so we want the variables to match. This is a definite integral. We know the answer is going to be numeric. It's not going to have any variables in it. So since we've already changed our limits to the world of theta, we can just compute everything in the world of theta. If we didn't change our limits, we would have to go back to the world of x's and use the limits from the x world and simplify. Either way, we'll get the same answer. So here we're sticking in the world of thetas, just plugging in our limits as given, and let's compute this out. Tangent of pi over 6. So that's equal to sine of pi over 6 over cosine of pi over 6. Sine of pi over 6 is equal to 1/2, and then cosine of pi over 6 is equal to square root of 3 over 2. So this is 1/2 divided by the square root of 3 over 2, which is equal to 1 over the square root of 3, but if you like to make your denominators nice, that's just equal to the square root of 3 over 3. Tangent of 0 is sine of 0 over cosine of 0. Sine of 0 is 0, so that's equal to 0. Minus pi over 3 times pi over 6. Simplify this a bit further. Square root of 3 times square root of 3 over 3 is equal to 1. And we subtract from that pi times the square root of 3 over 6. That is our final answer. Another beautiful problem, and you can see techniques are building on each other again. This borrows stuff from the previous video on trig power integration. But there you go. As you can see, the pattern is the same, where we use the triangle to make substitutions, and then integrate from there. In this case, we didn't have to switch back to the world of x's because it's a definite integral. Cool. Let's do one last problem. The integral of the square root of 1 minus x squared over x to the 4th. And then, you would go down your checklist of like, does U substitution work? No, it's not going to work. Does integration by parts work? Maybe, but that just seems super annoying. Not any trig powers because there's no sines, cosines, or anything like that. So now we're starting to think trig substitution, and it's a good idea because we see that this is of the form a squared minus u squared, right? 1 minus x squared is equal to the square root of a squared minus u squared when a equals 1 and u equals x. As always, we can draw our triangle here. That's a right triangle, throw in a theta. And then we have to be creative with how we're placing our side lengths. So we know that this side length 1 minus x squared will not be the hypotenuse because it's not a plus sign. That just comes with practice and knowledge of the Pythagorean theorem. So we'll put that as one of the legs. The other two legs will be 1 and x, and you can play around with it, and you'll see that the hypotenuse is 1, and the other leg is x. If we scroll back up, we are under this column here, which indicates we should take the sine of theta and the cosine of theta. So let's do that. Sine of theta is equal to opposite over hypotenuse, so that's just x over 1, which is x. And then cosine of theta is equal to adjacent over hypotenuse, so that's square root of 1 minus x squared over 1, which is just square root of 1 minus x squared. Cool. So we can substitute this in. We know that's equal to cosine of theta. We can substitute for this because we know what x is equal to, so we just raise that to the 4th power. We still need to substitute dx, so for that we can take the derivative of both sides of this to get cosine of theta d theta equals dx. And now we're ready for some substitution. Let's rewrite this integral with colors. So the numerator stays 1 minus x squared. In the denominator, we'll use this blue color, x to the 4th, and then dx will be in pink. And now we can see how things line up with each other, and we're ready to substitute. So this becomes the integral of cosine of theta divided by x is sine of theta, so this will be sine to the 4th of theta, and dx is equal to cosine theta d theta. If we clean this up a little bit, this is cosine squared of theta divided by sine to the 4th of theta, d theta. That's what we have to work with here. Okay, so this isn't particularly fun to work with, and we can go back to the trig power video and go through the checklist, but we can also be a little bit creative. This is equal to cosine squared of theta divided by sine squared of theta times 1 over sine squared of theta, d theta, just sort of breaking apart that sine to the 4th of theta. And now we can represent it in terms of non-sine and cosine functions. Because cosine over sine is cotangent, so that'll be cotangent squared theta times 1 over sine squared theta will be cosecant squared of theta, d theta, which is slightly more aesthetically pleasing to work with, and this can actually be solved using some U substitution. If we let U equal cotangent of theta, then du will equal negative cosecant squared of theta, d theta. So that makes the integral equivalent to u squared times cosecant squared of theta times du over negative cosecant squared of theta. We see that the cosecants will cancel. We're left with negative integral u squared du, which is equal to negative 1/3 u cubed. We have to substitute in for u, so this is negative 1/3 cotangent cubed of theta plus c. But lastly, we have to switch back to the world of x's because it's an indefinite integral, and we were given it in terms of x. So how do we compute theta here? Well, we're looking for cotangent of theta cubed, so we can look at this triangle here to compute cotangent of theta. So cotangent of theta is going to be adjacent over opposite. Adjacent is the square root of 1 minus x squared. Opposite is x. So we can substitute in by saying this is equal to negative 1/3 times the quantity 1 minus x squared over x raised to the third power plus c. Box your answer and call it a day. There you go. 3 examples using trig substitution. We went through all 3 forms of the like a squared minus u squared thing that you're looking for, but you can see that they're all very similar to each other in what you're trying to do. Build the triangle, find sine of theta, cosine theta, or secant of theta, tangent of theta. Change everything into thetas, and then integrate from there. Switch back to x if necessary. But there you go. This is one of like my favorite techniques because of how beautiful it is. I was really bad at it when I first learned it, so being able to detect it and follow this pattern will put you in prime position to do well with these integrals. In the next video, we are going to turn to what is actually my absolute favorite integration technique. I'm so excited for that one, so I hope you're looking forward to it as well, and I will see you then. As always, I hope you have a good day, and take care.